In this short video, I would like to show how we can find the enthalpy of reaction indirectly using Hess's law. So we're going to use Hess's law, which really allows us to take and move away from an experimental approach to finding the heat of reaction to just using some tabulated data for particular reactions. So let's put out there the reaction we'd like to know the enthalpy of reaction for. Ammonium nitrate as a solid going to a lot of gases, 2N2 gas plus our O2 gas plus water as gas. So if we wanted to know the enthalpy of reaction for this particular reaction, we could go to the lab, or what we can do is go to the tables, or go to tables where they have reported for particular reactions, usually from elements to compounds, heat of formation, and build indirectly build this particular reaction. So I'd like to show how we can do that. So let's take some reactions that we'll use to indirectly, through Hess's law, build our reaction and thus know the enthalpy of reaction. So from a table we can find that from elements, N2 as gas plus oxygen as gas plus hydrogen as gas, we can make ammonium nitrate. Now I'm going to put to the side here the amount roughly of kilojoules of energy that's kicked off if it's a negative, or taken in if it's positive, for this reaction. Now notice I have just one ammonium nitrate. For standard heats of formation of a compound from their standard elemental states, it's usually for 1 mole. So I've left it as that, and we've had to switch oxygen then to 1.5, because 1.5 times 2 is 3, and we need 3 oxygens on the left, and since we have 3 on the right. So that's our first reaction that we'll use to again make this reaction up here that we can build from 2. We're going to build this reaction that we want to know the enthalpy of reaction for. So let's show the next one. H2 plus 0.5 O2 gives us H2O as a gas. The enthalpy for this reaction is minus 241, or 242 roughly, 241.8. So what we're going to do now is we're going to rearrange this so that we have this equation here, and we're going to add these two. So we're going to rearrange if we need to, multiply by whole numbers. So let's notice here that we do have water on the right side of the arrow, reaction arrow. So this one's going to be okay, but we need a number, we need to add to the number of water that we have, multiply by 4, because we need 4 water molecules on the right. So what I'm going to do below here is I'm going to write this one here first. So I'm going to multiply by 4. So we'll have 4H2, 0.5 times 4 is 2, and we'll now have 4H2O. I'm going to leave off the phases, and this was from gas and gas. I didn't show that. But what we're going to have to do now is multiply 242 times 4, minus 242, meaning it gives off heat. We have to multiply this enthalpy of formation of water, enthalpy of formation from the elements to make water is minus 242. But to make 4 moles of water instead of 1 mole of water, we need to multiply the heat of formation of water by 4. Okay, so that gets us our 4 water molecules on the right. But we notice the ammonium nitrate in our, I guess, standard heat of formation table, or the table that reports standard heat of formation. We notice the ammonium nitrate's on the right. We need it on the left. So whenever you do a inverse or flipping of the equation, you need to flip the sign. So I'm going to write it down here, not just as NH4 and O3, but I need 2 of them. So I'm going to multiply everything by 2. So I'm not only going to flip it over, product goes to the reagent side, reagent goes to the product side, but I'm going to multiply it by 2. So we're going to have 2 N2, and I'm again going to leave off the descriptors for the phase. We have 3O2, that's 1.5 times 2, and we have 4H2. And if we again flip it, we have to have a positive 366, sorry. We have a positive because we flipped this over. And we also need to double it, so we're going to multiply it by 2. Let's see if we can get everything to add up then, these two equations to add up in a sense to what we have up here. Now carrying it down, we notice that there's nothing to cancel on this side with ammonium nitrate. So I'm going to have 2 NH4 and O3 on the left side. Now I do want to notice though the 4H2 cancels with the 4H2, so that's out. And there are 2 O2s in the left and 3 O2s on the right, so in the end there's not going to be any O2 on the left side of this equation, or reaction arrow, because it's been canceled out by the 3 on the other side. So what we get then is we get still 2 N2, because there's nothing canceling that out. But here we get O2 because we have 2 that cancels out 2 of this 3, but we have 1 remaining, plus the 4H2O that also carries down. Again, on the right side of this reaction arrow, it carries. The oxygen came to the right side because only 2 canceled out 2 of the 3 here. And then the 4H2 on the left up top canceled out with a 4H2 on the right side of this equation. But nothing canceled out with the ammonium nitrate. And voila, if we look to the top, these two are the same. Indirect way of coming to the heat of formation, and all we would do is add these two kilojoules up. We'd take 4 times minus 242, and that'd be a negative number, and add to that 2 times 366. So it would be what we do with the math. That's it. That's how we use Hess's law to find the enthalpy of a reaction indirectly without going to experimentation. We can go to tables, find equations from which we can build the reaction we're wanting to look at. That's it. Bye-bye.